record and you can fire away. Thank you.
Okay, thank you everyone online for joining us and for those in the room today. My talk is Alice Through the Looking Glass, Making Sense of Feature Space. What Alice saw through the looking glass was a strange world indeed, populated by eccentric characters like the Mad Hatter, the March Hare, and Humpty Dumpty. It was a strange world where there were frequent changes of time and space, but reversals and time running backwards. The country, according to the Red Queen, was like a chessboard, regular and as laid out there. And the poems were stranger still. What I want to suggest to you today is that Wonderland is a little bit like latent space, which we as mathematicians and computer scientists have often used. I think that in particular, I want to show that these latent spaces, particularly formed by deep neural networks, are not quite the black boxes that they are often made out to be. Indeed, there have been recent developments which have made this latent space more regular, and it might in fact be more understandable than we might first have imagined. And I want to show how important it is to make sense of this strange place called latent space, or what I shall call in this talk as feature space. For my previous research in a PhD, I was able to study this, and I, in my postdoc work, will continue this work further. And I want to show how these techniques may in fact have wider applicability, and that is why I think my research is important. Now, let us go back and start. Well, where shall we start? We should start at the beginning. Today, with the advance of technology being what it is, we are presented with ever larger data sets. And there's often a great need to be able to make sense of them. And we do that by usually a dimensional reduction technique. That allows us to extract what we think are the key features, the essential features of the data, and be able to analyze them further. Now, one of the oldest techniques going back 80 years, of course, is principal component analysis. And I use that in my research previously in my PhD. And I use a functional version of that. And here you can see an example of what these principal components are. As a functional component, they describe modes of variation. And what we have here is where I was studying vertical ground reaction force in a vertical jump. And here we have the color coding. We see that red coloring here indicates a higher performance and blue a lower performance. And you can see in the respective components here that the curve waves around a certain point. And so we know by recognizing, for example, here, that if we see a curve that has this initial peak here before the second peak, that is a sign of better performance. But principal component analysis is limited in the sense that it's a linear decomposition, so it's unsophisticated and it's not able to deal with temporal variations. We need to have the curves properly aligned with one another so that amplitude variation becomes apparent. So therefore, we need to look to a more sophisticated techniques. Now I want to go back to the 1980s, in fact, where deep neural networks first as autoencoders were proposed here. And we start here, if you look on the diagram, imagine that you have an input data here, the nodes in blue. The data passes through the network, through this red bottleneck, and is reconstructed on the outside. And what the network has to do is it has to learn a lower dimensional representation of the data. It's forced to identify the key features that are important. But as it has an advantage over PCA in that it can construct non-linear manifolds in feature space, whereas PCA would have hyperplanes. So it can be more sophisticated, but very often real data follows a non-linear manifold. Now, here it is represented in a more abstract form and schematic form, where we start with real data X, which goes through an encoding function to produce a feature encoding Z. And then the decoder function, it attempts to reconstruct the synthetic data like that. Now, these work reasonably well with signal processing, for example, but when it came to, for example, trying to extract the essential features of an image, the reconstructed image was blurred. So this is a fairly old technique now. There were developments more recently, but it has not been as successful as the next example, the generative adversarial network. Invented in 2014, only 7 years ago, it has achieved much better results. It was first developed in the realm of image processing, and the images, as I will show you in a second, are quite astonishing in their realism. It starts from a different premise from the autoencoder. The autoencoder worked by the notion that it tried to improve the accuracy of its reconstructions by comparing the constructed image directly with the original image. And so in that sense, it was like a mean squared error. Whereas the generative adversarial network works on a different principle. Instead of comparing the generated synthetic data shown here in the slide with the real data, we have instead a separate network called the discriminator, which compares between the two. And there's a feedback loop, without getting into the technical detail, that allows the generator to learn from that. These two networks work together, but as adversaries between one another. And the best example, I think, of how they work is to think of it like this. Imagine your generator is an art forger, a painter who is quite gifted, and he wishes to recreate a Rembrandt, for example. And his job is to try to fool the art expert into thinking that his fake Rembrandt is in fact a real one. But the art expert, on the other hand, has got to be able to learn to distinguish between the fake and the real one. Initially, they both start making poor representation of the Rembrandt, and the art expert is pretty hopeless as well. But by working together in an adversarial manner, inspired by game theory through a min-max game based on this loss function here at the end, the generator is able to achieve quite impressive images. Let me just show you this. So what we've got here on the left, we've got images of rooms that have been generated. The network has learned from a whole data set of room pictures, but it's given a random input and it generates a new room, a new synthetic room. And as you can see here, they have astonishing realism. There's something you can do more. You can regularize this feature space. What you can do is you can add conditions. You can condition the probability distribution. And so here with InfoGAN, another type of generative adversarial network, you can have conditions or labels about the particular image itself. For example, the orientation of the chairs or the width of the chairs, for example. And here's the really interesting thing. If you take 2 points randomly chosen in feature space and you interpolate between those points, then you get a regular stepping stone from one position to the other. And so by moving between these different these factors here, we can orientate the image as we see fit. So from my point of view, when I'm looking at feature space, I see here a regularized space, something that we can start to make sense of. And what I did in my PhD work was that I was able to show that those features, those functional principal components from the ground reaction force data, or eventually I've studied accelerometer data, that they in fact were related to the performance of the jump. So I see here an exciting opportunity to be able to do this regularized, take advantage of the regularized feature space in order to start to understand performance. But there's one key element to this that's missing. You see, I have shown you here an ability of a network to generate an image. It could generate other things as well. But what I need to do is the opposite. I need to invert the generator function. Because I will have real data. And what I want to do is I need to take that real data and get an encoding of it. And because these GANs have learned what is the essential features of whatever they've been trained on, what we can do is we can make use of the discriminator who's learned to distinguish, like our expert between what is a real Rembrandt and what is a fake Rembrandt. And we can use that learning from the discriminator. But I need to start first with an inverse. Now, fortunately, this has been established. The bidirectional GAN was proposed in 2017. In fact, there were 2 or 3 independent developments of the same technique. And it also went by the name of adversarial learned inference. After all, that's what I'm trying to do with my data. I'm trying to infer what are the essential features of that data, so I can then use those features in some other model itself, for example, related to the performance or whatever outcome I'm particularly interested in how that's achieved. Now, we can do a little bit better than that. You see, if we also introduce another term into the loss function, the entropy, what we can do is we can maximize the separation between the classes within feature space. And that leads us to ALICE, adversarial learned inference with cross entropy. And that inspired us to the title of my talk. So let me outline where I see myself going with this. So there's a more sophisticated representation of the features in data itself. About 90% of the work thus far in the field has been focused on images. There's been other work that's been focused on natural language processing or audio processing, but I want to take it in a different direction. I want to take it into analyzing inertial sensor data, or other sensors for that matter as well. I want to look at time series data. Now, there are network types that those in computer science will be familiar with, for example, the LSTMs, the long short-term memory networks, that may be suitable in this regard. That's one element of it. But the thing that is unique about my research is what I then do subsequently with that information. So when I learn the features, I want to be able to develop a model that then relates that to performance outcome. But that's not quite good enough, because there may be some abstruse relationship that does exist. But to practitioners who may be using these models, for example, with sports science, from where I have come, they need to be able to make sense of these features. Now, we can go actually some way to do that. And the images that I showed you earlier shows that there is some regularization. What we can do is we can condition the probability distributions in such a way so that there is a feature space without gaps in it, that it follows a regular pattern that can be more understandable. But where I need to investigate further in my research, and I don't have the answers just yet, is I need to be able to construct something along the lines of what the functional principal components were able to do, that they had variations that were intuitive, immediately understandable, even to the non-expert. Now, that might be possible by exploring feature space, perhaps by constructing a surrogate model that approximates the function of the generator network. That might allow, for example, to optimize the surrogate model in order to, for example, maximize performance. If we have a conditional variable that is associated with performance, we could maximize for that. Alternatively, if that's not part of the original function, we could have a subsequent auxiliary function that looks at the generated output and then computes the performance outcome, and thereby we can have this second stage inference. So there are different ways in which I'm sort of looking at that. But if we have here on the right, we have something here from the NNIST data set where a number 9 was translated vertically up and down. You can see that there's some sort of regular pattern. That's where I want to take this further. So to return to the theme of my talk and to Lewis Carroll, the Jabberwocky poem. Now, Alice was able to deduce, and did you, that the key to this is it is actually a mirror image. And here are the text itself. But my goodness, 'twas brillig and the slithy toes did gyre and gimble in the wave, and oh, mimsy were borogoves and the mom raths outgrave. What on earth does that mean? And Alice concluded that somehow it seems to fill my head with ideas, only I don't know exactly what they are. But I think that there is a way that we can do this with latent space, that by regularizing it and by attaching additional models to it, we can actually go further than what Alice was able to do. And I think this applies not just to sports science, where my work will be, but can have a much wider applicability. Thank you for listening.
Thank you very much. Thank you, Mark. That was great. We've got a few hand claps on the screen as well. Bless Mark, with the technology today, you can't actually see the Zoom screen, but I'm sure you'll be able to hear everyone. If anyone's got any questions or anything like that for Mark, I will stop the recording now and then we can go on to question and answers. Thank you, guys.